Alright, today we're going to be talking about direct and then limit comparison due to the fact that they are very intertwined. But first off, we're going to start off with direct comparison. Now I'm going to put up an example problem up on the board. Alright. This is our starting series. The first thing that you would first try to learn would be nth term test, which is a very simple test since it is simply taking the limit. However, when we take the limit at infinity, it's 0 and the test fails. So, what you do next is the direct comparison test. And with the direct comparison test, there are 3 steps. The first step is, first off, examining the original series and creating a test series that is either a harmonic or p-series that would be easy to test the convergence or divergence. Now, for this series, an easy test series would be same bounds, however 1 over n squared. Now, for this is testing the convergence. And to test the convergence, you must choose a test series that is larger than the original. Simply think of it as like holding down the original series. And the easiest way to think of that is by using a graph. Since this is our original, you can think of this one being the test series. And see, the test series is holding down the original series. That's kind of the easy way to remember it. Now, back to the first example. You've chosen your test series. Now what you must do and set up the inequality. Now, for testing convergence, like I said, this one is larger than this one. So, alright, that's step 2. Now step 3 would be testing the test series for either convergence or divergence, as you decided originally. Now for this, obviously we are testing convergence since the test series is larger than the original series. Luckily, this series right here is a p-series. And in this case, it's, let's see, obviously in this case, p is equal to 2. And since when p is greater than 1, the series converges, this series converges. And now since this series is larger than this series, and going back to the graph, the test series is larger than the original. That means if a larger series is convergent, the smaller series is convergent as well. Simply because the larger convergent series is holding the smaller convergent series to a finite number. Now, the next way to test for using direct comparison would be testing for divergence. So for this one, we're going to use this series right here. Alright. Now, this one, if you were to try the nth term test, would come out to 0, meaning the test is inconclusive. Now to test the divergence of this one, you need to set up an inequality, or choose a test series so that the inequality means that this one ends up being larger than the test series. So in that case, alright, decided to change that one right there because, well, because I felt like it. So now testing this one, this is another p-series. However, since p right here is equal to 1/3, and p is less than 1, that means that it is divergent, which in this case holds the inequality true. Now the reason that makes sense is I'm going to go back to the graph example that I had in the convergent test. Just make it a little bit bigger so it's easier to see. Now let's say we had one series right here, and we wanted to test the divergence of that one. The problem is doing the nth term test, it comes out to 0 and is inconclusive. Easy way to do it is to test a series that would be smaller than the original. Because if a small series is divergent, then the bigger series is going to be divergent as well. Think of it basically as the small series pushing up the original larger series. That's the easy way to remember testing divergence. Now, alright, to continue on with our lesson with direct comparison, I have a couple of example problems up on the board that we can work through to get ourselves a little more familiar with the process. Now, in this, with this series right here, what I'm going to do is test the convergence due to the fact that we have an n value in the denominator, meaning it would be more likely to be convergent than divergent. So, to test a convergent series, you would choose a series that would be larger. And in this case, I'm choosing 1/4 to the n to keep it simple. Now, this series is very similar, actually it is the exact same thing as the geometric series 1/4 to the n. Now, in this case, if you were to solve it, it would be 1 plus 1 to the 4th plus 1 to the 16th. Now, you're multiplying by 1/4 every time, and the number you're multiplying each value by if this number is less than 1, that means that this series is convergent. So that means that this one is convergent. Now, in that case, this series would also be convergent since it is smaller, going back to the graph example, which would mean this one would converge by the direct comparison test. Alright, there we go. Alright, let's move on to this problem over here. Now, in this case, see if we can test the divergence, since this one appears to be a lot different than this one due to the fact that the greater n value is in the numerator as opposed to the denominator. So, testing this, try to get rid of the coefficients to avoid any confusion. It would be 4 to the n or 3 to the n, which is very similar, actually it is the exact same thing as I said before, to the series 4/3 to the n. Now, if this series was to be added out, the value that you would multiply every single n value by would be 4/3. Now 4/3 is greater than 1, which means that the series diverges. So this one is divergent, which translated over to this series means that this one is also divergent by the comparison test, direct comparison test. All right. Now, let us try a different one. We're going to all this fun stuff. Now, try something a little more complicated. All right. Let's try to do this one by direct comparison. Now, with the 5n and the 2n to the fourth, those are the two values we need to worry about. Like I said previously, coefficients aren't something we necessarily need to worry about. They're just kind of thrown in to confuse you. In this case, to test the convergence, you would have to choose a series that would be greater. Now, since the n's cancel out, it would be 1 over n cubed. However, here's the problem. As I said before, with avoiding the coefficients and the constants, this series when simplified would end up being 5/2 times 1 over n cubed. And we're saying that that's less than 1 over n cubed. And last I checked, 5 over 2 is not less than 1, meaning that this inequality proves wrong. However, when a direct comparison test fails, the next step to take would be the limit comparison, where you take the limit as n approaches infinity of the ratio of the original test and the test series. The original series and then the test series. So that set up would look a little something like this. Voila. Now, multiply this out. Take the limit, and ends up going out to 5/2. When doing the limit comparison test, if the limit value comes out to be a finite positive number, the inequality in the original equation ends up being true. So in this case, series converges by limit comparison. And divergence. Now, for these, they could go limit or direct comparison. So I decided to throw a few in there that are a bit different to make it a little interesting. Now, we're going to go reading like a book, left to right, top to bottom. Meaning we're going to start with this one. Now, with this one right here, due to the fact that the n values are down at the bottom, we're going to test for convergence. So obviously with convergence, you would set up a series that would be larger. 1 over 3 to the n. Now, that one is the exact same thing as 1 over 3 to the n, since n to any power is, or excuse me, since 1 to any power is simply 1. In this case, 1/3, in this geometric series, 1/3 is the number being multiplied by every single n value. So, and since 1/3 is less than 1, basically this one converges by the geometric series test. Consequently, the original series converges by direct comparison. Alright, set up, yes, you'd set up a series that would be smaller than the original. Now, since the two n values that we had to pay attention to, the highest power on the numerator and the highest power on the denominator, would be 2n in the numerator and then n squared in the denominator. Now, if you were to simplify that out, it would come out to 1 over n, simply ignoring the coefficient on the 2, since 2 is obviously greater than 1. Now, looking at this, this is a harmonic p-series that diverges. So this one would be divergent, and consequently, this one would be divergent by direct comparison. Alright, now, this next series right here, we are going to go ahead and test the convergence. So, for convergence, you would choose a series that would be larger. Now, you take the two n values, you get 8 to the n over, or excuse me, 8 times n over n to the third power. If you ignore the coefficient, it would be 1 over n squared. However, the issue with this is, you simplify out 8n over n to the cubed, it would be 8 over n squared. But 8 over n squared, when set up into an an inequality like this, does not hold true. So, in this case, you'd have to do limit comparison. So you take the limit as n approaches infinity of the original times the reciprocal of the test. So that would come out to 8n cubed plus n squared over n cubed plus n over 3. Alright. Now, when you take the limit of that, since these two are the same power, they cancel out, and then these don't really matter when you're taking the limit when n equals infinity, since the highest power is the one you have to worry about. That would equal 8. And since that is a finite, non-negative number, that means that this series, this one right here, would converge by the limit comparison test.